Alright guys, so we are starting section 1.5. This has to do with vertical asymptotes and what happens as we approach vertical asymptotes. What you need to know about with respect to graphing these is what's going to happen if we have a function like 1 over x. We know if the denominator will equal 0 for some x, then we're going to have a vertical asymptote. So what's going to make the denominator 0? 0, right? So if I were to graph this function, there has to be a vertical asymptote here at 0. And as we approach a vertical asymptote, one of two things has to happen. Either the function is going to shoot way up to infinity, or the function is going to shoot way down to infinity. To find limits, we always plug in the x value. But if I asked you to do the limit as x approaches 0 for 1 over x, what's going to happen? What are you going to get? Does not exist. So the general limit as we approach a vertical asymptote does not exist. But it's very helpful to know what happens to the graph as we get closer and closer to 0. So if I asked you what's the limit as x approaches 0 from the negative side, maybe, how would we know if it's negative infinity or positive infinity? We would have to just plug in a number that's really, really close to 0, but just a little bit smaller. So here's 0. What's a number that's just a little bit smaller than 0? Right, so if I plug that in, I would have 1 over negative 0.0001. If I do that on my calculator, you should be able to do it without, but if I use my calculator, 1 divided by negative 0.0001 is negative 10,000. So does that support the fact that we think it's negative infinity? Yeah. So as we get closer and closer to this asymptote, it's approaching negative infinity. Okay, we'll do the next one without the calculator. So now we want to know what's the limit as x approaches 0 from the positive side. Well, now I have to think what's something a little bit bigger than 0. Yep, 0.0001. Instead of using my calculator, I'm going to multiply the denominator by 10, 100, 1,000, 10,000. So I'm going to multiply the numerator by 10,000. And I would get 10,000 over 1, which is positive 10,000, which means that it's going up to infinity. All right? So that's the type of thing we're going to be doing here. So the first question is, when does a function have a vertical asymptote? When's that going to happen? Whenever the denominator equals 0. So when denominator equals 0, and another thing has to happen, and that is, and does not cancel with the numerator. So when we have a factor that's going to cause our denominator equal 0, and that factor does not cancel with the numerator, that means we have a vertical asymptote. What type of continuity is found at a vertical asymptote? We have three options: continuous, removable discontinuity, or non-removable discontinuity. Non-removable. So it's a non-removable discontinuity. And anytime we have a non-removable discontinuity, we're going to know that the limit does not exist. So anytime a function is approaching a vertical asymptote, the limit does not exist. However, the behavior of the limit can be described by using values of infinity or negative infinity, like I just showed you a minute ago. Here are some important things to remember. Anytime I have a constant divided by 0.0001, we just did that on our calculator. If I have any constant, let's say 6 divided by 0.00001, I'll even add in a few more zeros. See how that's infinity? That's what that means. That number is getting infinitely larger. If I add on even another 0, or a couple more zeros, see what happens? It gets bigger and bigger and bigger. So that's why it's approaching infinity. But if we have a constant divided by negative 0.0001, that's going to be negative infinity. All right, so let's do a few examples on our own now. So if our function is 1 over x minus 1, find the following. What is the vertical asymptote? Sandra, what's the vertical asymptote going to be? X equals 1. Good. So now we're supposed to find the limit as x approaches 1 from the negative side. Now I could just type this into my calculator, this function, and look at it and see, but we don't want to do it that way. We want to use a more sophisticated method to do this. So we're going to plug in a number just a little bit smaller than 1 because we want to know from the negative side. So what's a number a little bit smaller? Blake? Yep, so we're going to do 0.999 minus 1. So I plug that in and I get 1 over, this is going to be 0.001. And what's that going to be the same as, everyone? Infinity. So the limit as we approach 1 from the negative side is infinity. Now we want to test a number really close to 1 but slightly larger. Calvin, what's that going to be? And if I do that, I have 1 in the numerator. 1.001 minus 1 is 0.001. I'm sorry, this should have been what? Negative, thank you. And this one is going to be 0.001. And so this is going to be our positive infinity here. So I made that mistake, but if I had gone back and checked this, hopefully we would have caught it. Because 1 divided by x minus 1, if I even just look at this graph, oops, I forgot to take out my other function. If I put in 1 divided by parentheses x minus 1, here's the way it looks. So I can see that as I approach 1 from the negative side, it's going to negative infinity. As we approach 1 from the positive side, we're going to positive infinity. So is it always the case that one of these has to be negative infinity and one is positive infinity? Well, let's see on the next one. It says find the limits as x approaches the vertical asymptotes from the left and as x approaches the vertical asymptotes from the right. So, Emily, what are the vertical asymptote? What's the vertical asymptote going to be? Right? So our vertical asymptote is x equals 3. So they are asking us to find the limit as x approaches 3 from the left of the function. So to do that, I have to plug in a number that's really close to 3 but not equal to it, because I can't plug in 3 or I get undefined. So I'm going to plug in 2.99. If I do that, 2.999 minus 3 is going to be negative 0.01. But then if I square it, well, if I square a negative, it's going to become a positive. And all that happens to the decimal is I get twice as many numbers. So if I have 2 numbers after the decimal, I'm going to get 1, 2, 3, 4. And so what's that limit going to be then? Infinity. So the limit as x approaches 3 from the negative side of the function is infinity. And now we're going to find the limit as x approaches 3 from the positive side. So now I have to plug in something a little bit bigger than 3, like 3.001. You can use as many zeros as you want. You don't have to use, like I'm just using 2 here, or 1 0 rather. So I'm going to have 1 over 0.01 squared. That's going to be 1 over 0.001. And so what's that answer going to be? Infinity again. All right, so what we want to see here is that it's not always the case that one's positive infinity and one's negative infinity. Sometimes we have both of them as infinity. So if I look at this graph just to check it, here's the way this one looks. Did I type that in? I keep forgetting with my new calculator that I have to go over here to type it in. Here we go. So it looks like this. So can you see how as we approach 3 from the negative side and from the positive side it's approaching infinity? Okay. What do you think is causing that to happen? The squared, right? Yeah. All right. Use the function below to describe when a function has a hole in the graph and when the function has a vertical asymptote. If we have a hole in the graph, what has to happen? Megan? Right. So to have a hole in the graph, that's going to happen when f of x equals g of x or f of x equals h of x. But what else would have to be true for there to be a hole there? They also must be capable of equaling 0, right? And equal 0 for some x. Because we could have a function, see look, I could have something like this, x squared plus 1 times x over x squared plus 1. These two are the same, but there really is no hole in the graph because these could never equal 0. X squared is positive. If I add 1, that's still going to be positive. It can never be 0. All right? So that's something we have to make note of. To have a vertical asymptote, g of x and or h of x equals 0. But they can't cancel, right? Because if they do cancel, it's a hole. So we can say g of x and or h of x equals 0, but do not cancel with numerator. Or in other words, they do not equal f of x. All right. Use the function below to find vertical asymptotes and holes in the graph. So how do we approach that? Gage, what would I do to find all of that? Yeah, just factor. How's the numerator factor, Gage?
X plus 4.
In the denominator?
X plus 2, x minus 2.
So these two cancel. So what does that mean we have right there? Hole. Now, here's how I want you to write the holes, guys. There's a hole at 2, comma. Now, to find out the y value that goes with 2, we plug into what's left over. 2 plus 4 is 6. 2 plus 2 is 4. 6 over 4 is 3/2. I want you to find the exact coordinates of the hole in the graph. Again, all I do is 2 would make those equal 0, but they cancel out. I plug 2 into what's left over. The reason I want you to do that is because it also tells us the limit of m of x as x approaches 2. See, now I know that limit. That answer to that limit is 3/2. Because it's just going to be equal to the value, the y value of the hole there. All right? Vertical asymptote, where's that going to be? Tyler? Say it again?
2.
No? What makes this equal 0?
Okay.
-2. So it's going to be a vertical asymptote of x equals -2. Any questions on that? All right. Find all vertical asymptotes, which are called non-removable discontinuities, and holes, which are called removable discontinuities, in each of the graphs. All right, so take a look at the first one. What are we just going to have there? Olivia? It does not cancel, so what's it going to be if it does not cancel? No. If it makes the denominator equal 0? Go back up here and look. If it makes the denominator equal 0, right here, makes the denominator equal 0, it's going to be a what? What is it, you guys? Vertical asymptote. It's a vertical asymptote. If it does not cancel with the numerator, it's a vertical asymptote at x equals -1. Guys, if you're not sure about something like that, go to your graphing calculator. Let's say you can't think about, and look at this too, guys. I have to make sure that the entire denominator is in parentheses. So I had to do 1 divided by the quantity of 2 parentheses x plus 1. And now when I graph it, here's the way it looks. Can you see how there's a vertical asymptote there at -1? It's not a hole in the graph. See, I let you use your graphing calculators on almost everything, so you should be checking with them. All right, especially if you get confused on something. Now, I will warn you that I've heard some colleges in their calculus classes, they don't allow graphing calculators at all. Ohio State is kind of notorious for that, a lot of their calculus classes are non-graphing calculator. And the reason they do that is because so many students go in there knowing how to do so much on their graphing calculator that they really don't have to know any calculus because they can do so much of this without knowing calculus. All right, let's look at number 2, though. So we're trying to find any vertical asymptotes or holes. So we factor the denominator. Do we know how that factors? What is it, everybody? All right. Does the numerator factor? No, not if it's x squared plus 1. That cannot be factored. So therefore, what are we going to have? Right, 2 vertical asymptotes. And let's say you're not understanding that and you think, well, I don't know what that means when that happens. Well, you can just look at it on your calculator. And when you type this in, you're going to see that there are 2 vertical asymptotes. See how it looks? There's actually 2 of them. One of them right there at -1, one right there at +1. All right, last thing, cotangent. Do you guys remember how cotangent looks? Can anybody describe it? Calvin, you're nodding. Okay, he's right. And because of this 0, that helps me remember that the cotangent goes down. And he was saying it's going to go down like this, which I agree with. Where's the first vertical asymptote, though? Does anyone remember that? At 0. I remember that because of that 0 right there, that O. And I also should remember that the period here is pi. So here's the way the cotangent graph looks. So I know that I'm going to have vertical asymptotes at x equals -pi, ... this way, 0, pi, ... That's one way of writing it. Or I can say x equals pi k, where k is an integer. Because I can do 0 times pi, 2 times pi, 3 times pi, 4 times pi, etc., and -1 times pi. Now, let's say you didn't know that. Well, how would I put in cotangent? 1 divided by what? Tangent. And I want to do a zoom trig, which is a zoom 7. And here I can see the cotangent curve. And I can see those vertical asymptotes at 0, pi, 2 pi, -pi, -2 pi. All right? So either way, you want to write those vertical asymptotes. All right, any questions? So your homework is going to be asking you a lot about continuous versus discontinuous. And then they're also going to be asking you to find these limits as you approach vertical asymptotes. Remember, the answer is going to be infinity or negative infinity if you're approaching a vertical asymptote.